Hello everyone. Today I'm going to work on this problem. Uh, I chose this problem from the Mechanics of Materials by R.C. Hibbeler, 9th edition. It is just a problem that we can solve using the compatibility equation. Let's read the question. The rigid link is supported by pin at A and two A36 steel wires, each having an unstretched length of 12 inches and cross-sectional area of 0.0125 inch squared. Determine the force developed in the wires when the link supports the vertical load of 350 pounds. First of all, we have to draw a free body diagram for the structure. Because we have a pin at A, I can use this to show the vertical and horizontal reactions at A. So I can call them, for example, AY and AX. Also, we have two other reaction supports at C and B. So I choose this for TC and I call this TB. Okay. And also we have this external loading here. It is the free body diagram for the rigid link. So, if we just start to write the equilibrium equation or start to solve the statics of the problem, because I just want to find TC and TB, I mean this force and this force, tension in the these wires. I don't need to find AX and AY. So the base equilibrium equation that I can write is sigma m about point A equal 0, and I choose the counterclockwise as the positive direction. Why I choose this one? Because if I just write the sigma m about A, the moment of AX and AY about A is 0, so they don't enter into the equation, and just TC, TB, and this external loading enters to the equation. So if we go with TB, the moment of TB about this point A is clockwise. So I use a negative sign to show that the moment is clockwise, and the lever R is this distance that you see is 4 inches. So I just write this for the TB, and for TC I have negative TC. Why negative? Because TC also rotate about A clockwise. So negative TC times the lever arm in this case is 9 inches. So the other force that has a moment about A is this 350 pounds, but the rotation of this about A is counterclockwise. So I use a positive 350 pounds multiplied by, and this lever arm here is 6 inches. So it should be 0. Again, AX and AY has no moment about A. And if I just rearrange and simplify more from this, we can get this equation for TB. If I move this to other side, plus 9 TC equals 350 times 6. So if I multiplied 350 times 6, we get 2100. So I can just write 2100 pound inch. So as you see here, we cannot solve this. Why? Because we have one equation versus two unknowns. So this equation cannot be solved with two unknowns, and we call this a statically undeterminate problem. So to solve this, we need an extra equation, and this extra equation doesn't come from the statics or equilibrium. These extra equations comes from uh, compatibility. We call compatibility equation. And compatibility equations comes from the deformation of this structure. Because the link, this blue link is rigid, if we assume that there is a deformation for the link, I can draw this one. So if I choose a good color, I think this should be good. This link actually the formation of the link would be like this. Again, I don't use any scale, but I just want to show you the formation of the structure or the link, this rigid link, and I can use this to show the delta x and delta y. So this deformation or displacement we can assume for c, so we call this delta c. Also here we have this that we called delta b. Also actually we have here, but I don't need to find this, but actually we have also a delta here. So to find the compatibility equation, we have to find a relation between delta b and delta c. And to find a relation between delta b and delta c, if I use the angle theta, I mean if it was the vertical and the horizontal, we can define the angle theta here. As you see, we have angle here that we call theta, and this angle is exactly the angle that we have here. That is also theta. Okay, it is just the rotation of this link about theta. Because theta and other deformations are small, so because I can say the all deformation or displacement and rotations are very small. When we say very small, we mean compared to the original size of the structure. We can say the delta c is this side, I mean AC times theta, and also delta b is this distance AB times theta. And because the AC we are given as 9 inches, I just write 9 theta, and AB is 4 inches, I write 4 theta. Okay, why this is helpful? Because if I just divide these two equations by each other, I mean delta C over delta B, we get a 9 theta over 4 theta. And because theta is the same for both, I can just cancel out theta by theta. And what we get? We get this simple relation between delta C and delta B. So here we can just use the cross product and find this equation for delta C plus 9 delta B, is better to say 4 delta C equals 9 delta B. And we call this compatibility equation. And this compatibility equation actually help us to find extra equation that we need to solve TB and TC. To find the extra, I have to work with the formula that we had for the axial displacement. If you remember from the Hooke's law and axial loading, we have this, we can write this formula for delta C. Simply, I can say the deformation of this wire is delta C. And what is deformation of this wire? TC times L over E times L. And L is the same 12 inches. E just modulus of elasticity of A36 steel wires. And A is the cross-sectional that we are given. So because we are given this, we have E. Actually, also we are given the L, that is 12 inches. Also, we are given the cross-sectional area. And I can write a similar thing for delta B. Delta B is also the actual displacement of this wire. That is TB L over EA. And if you look at the question, you see exactly the L, the E, and the A are the same for both wires because they have the same material, A36 steel, the same cross-sectional area, and the same initial length, that is 12 inches. So if I just combine this by the equation that we found here, so we can write this formula. We can say for TCL over EA for delta C equals 9 delta B, that is TB L over EA. And the good thing here that you can cancel out E by E. You can cancel out A by A because they have the similar cross section. Also, you can cancel out L by L. And if they just cancel out everything, you get this equation 4TC equals 9TB. Okay, now we found our second equation. So we call this the equation, for example, 1. And we call this equation 2 that we get from compatibility. I just solve a system of equation using these two equations that we found. Equilibrium equations, that was 4TB plus 9TC equals 2100, and 4TC equals 9TB from the compatibility. Okay, you can use any method, elimination or substitution. For example, if I just isolate this for TC, we can find TC as 9 over 4 TB. I use the substitution method. So here I can replace TC with this value. I mean 9 over 4 TB equals 21 hundredths. Okay. To solve this, I can just factor out TB. So we get 4 plus 9 times 9 is 81 over 4 times TB equals 21 hundredths. And if I just isolate this for TB, TB would be 21 hundredths divided by 4 plus 81 over 4. Okay, so I just need to put everything on my calculator. So if I move calculator here, so you can see we have this expression over 4 plus 81 over 4. So we get actually to 3 significant digits. I can write 86.6, and the unit is the same unit of the force, that was pound. So it is the value of TB. Now we have to use this equation to find TC. So to find TC, I just write 9 over 4 times TB, that is 86.6. And if I just again use the calculator, you see here 9 over 4 multiplied by this value. So again, to 3 significant digits, I think 195 should be a good approximation for this one. So it is the TC and it is the TB. And again, we just solve this statically indeterminate problem using the equilibrium equation and compatibility equation. Thank you for watching and have a good one.